The next one, inverse function. Let f be a function from a to b. Given that f is a function from a to b, the inverse of f is another function g such that it mapped from b to a. That satisfies two properties. So if we have one function f, the inverse of f is another function which reverses the computation that is done by f. If f is a computation, g is another computation that reverses the computation by f. Similarly, f can reverse the computation done by g as well. So that kind of reverse computation is expressed by these two lines. The input of f is recovered by function g. Similarly, for the input of g can be recovered or reversed by the function f. So here are examples of the inverse of function. The similar one, the interesting case is this one. If f is if f defined by the exclusive or with some k particular key with the input x, the inverse of this function f is the same function with the same key actually. We know by self-cancellation property that identical to data, when you apply to exclusive or you get false, so it cancels itself. Okay. So similar to this to another function for inverse. If one function represents one computation, f one computation, g one computation, we can combine the two computations to get what we call composition of functions f and g. So the two composition is defined by applying g and then applying f. So these two consecutive execution of two computation is called composition of the two functions. I'm not going to the example, it's quite easy. Again, I'm going to skip this well, floor and seal function. Here are some interesting things. Suppose we want to look at the growth of function, the growth of different function, where the input to the function may be the size of data n. Let n be the size of data that is on this axis. Let the output of fn be the computation time that are required to process n data size. These are common growth rate. These are common growth of function which can describe different kind of time that are needed to process data. The first one is constant n f. This one describes one particular function which doesn't grow very much when the data size is increased. Whereas, for example, 2 power n will grow very quickly as the data size increases. So these different functions capture different kind of growth, which again capture different kind of computation time that are required to process data size. So we will come back to this when we discuss about the complexity of algorithm. But I like to point out that when fn defined by log n, we call this function logarithm function. The behavior or the growth rate, the growth of this function will grow like this. N will be a little bit more complex, but probably the most the fastest growth function is n factorial. Okay. Now we come to the second part of, it's not the second part, but it's second part of the first part. Okay, it is about recursion, sequence and relation. So Many of you have studied computer engineering before. You know about recursion, but some, have not studied computer before. So this would be a good foundation for you. Recursion. What does it mean by recursion? Recursion is a general way to define object in terms of itself. Okay. It is a technique to define object in terms of itself. So suppose you have many objects to define. If you want to define it one by one, if the set of objects are infinite, so you cannot define it one by one. So the easiest way or the trick is to define the object in terms of itself. So this recursion, you can use recursion to define many things: algorithm, function, set, or many other structure. Okay. The way to define recursive function consists of two steps. Okay, base case and recursive case. Suppose you want to define a function f on input, which is the set of natural number, whereas the output is any set, some set s. So you define the recursive function on the kind of data that it processes, the kind of input. So in this case, the input is set of natural number. So you can divide into two cases: the base case, the beginning, the first element of the data; the second, the recursive case. The base case, we define function f for the first element, which is 0. We just write down the definition for f. It depends on, the kind of computation that you want to define for f. But for recursive case, you define the function on n by using the function itself. But for the previous elements, okay, we define fn by itself, by function f itself, which is applied on the previous or earlier cases. So then, by this recursive, it helps us to generate infinitely many functions for data n. Okay. For example, if we look at the factorial of n, we will see that if we write down the definition of factorial of n, so it looks like this, and we see that this part of the definition is actually the factorial of something which is n minus 1. Then this gives us the idea that we can define the factorial function recursively. The base case is for the first element. The recursive case is when you define factorial of n in terms of the factorial of the previous case, which is n minus 1 in this case. นะฮะคือ recursive ก็คือเป็นการ define โดยใช้ตัวมันเองนะฮะแต่มันก็จะตัวมันเองอยู่กับที่ไม่ได้มันก็จะวนลูปไหมฮะคือเป็นการ define บน data ที่ก่อนหน้านั้นนะฮะคือมันจะเริ่มติดที่ตัวศูนย์ตัวถัดมาไปเรื่อยๆนะฮะคือ base case ก็คือกรณีแรกคือข้อมูลชิ้นแรก recursive case ก็คือเป็น n ใดๆ define บนคุณสามารถใช้ข้อมูลก่อนหน้าที่ n นะฮะในการกำหนดฟังก์ชัน f ตัวไหนก็ได้นะฮะอันนี้ก็เป็น recursive function ของ factorial นะครับ we can define very large set, infinite set by using recursion. Let S be the set of odd positive integer 1, 3, 5 and so on. It is infinite set. We can use recursion to define such infinite set. First, we state on the base case that 1 is in S. The recursive case will be this one. If I is in S, I plus 2 is in S. So we don't say that, we say that I plus, if I is in S, it's not a previous case, but it defines the membership of each element in terms of the membership itself. Okay, I plus 2 is in S if I is in S.